Okay, everyone, let's get started. Good morning. Okay, so I've got lab 1. The first project is assigned. I've got it on Dropbox here. So there's 3 links. There's the lab sheet, which is the first link. The skeleton, which is the archive you have to download and unpack in your home directory, is the second link. Third link's the submission box. I also have another quiz. Quiz 2 is due end of next week. Quiz 1 is due end of this week. And make sure you don't forget to take those. Okay, so lab 1, I talked about this a little bit last week. But the objective here is this is purely in software. There's no hardware involved. You're just writing software to read a trace file, which is basically a waveform stored in a text file, and interpret it as a series of SPI transactions. And then you just print out those transactions in kind of plain text. We give you a bunch of test cases, and we also give you an API to help you read that. And there's 3 parts. The first part is called 2 exchange transactions. So remember, a transaction is when you do a kind of a programmed I/O style read or write, where the master reads or writes to or from the slave. And there are 2 exchanges involved. I always get these mixed up, but an exchange is where you exchange 1 byte between both sides of the channel, and a transaction is when you do multiple exchanges to implement a read or write operation. So in part 1, you're just doing 2 exchange transactions, so read or write. In this case, you're going to assume that CFA and CPA are both 0, so you're going to stick to that one kind of hard-coded timing mode. Part 2 is where we introduce streaming transactions. So these involve multiple exchanges, and they allow you to read or write multiple bytes. So the idea is that the first exchange is a header, and then the second exchange is the length, and then the third and subsequent exchanges would be the data, which could be going one way or the other depending on if it was a read or write. Okay, and then part 3 is where the only thing that changes here is that you have to read the CPUL and CFA signals from the file and be able to deal with different timing modes. Okay, so your program will read those and then adjust accordingly. Okay, so let me real quick show you how. Let's go back. If you download the skeleton, and it's this tar.gz file, and I'm going to go ahead and connect to one of the lab machines here. 222 L-3D22-01. And hold on. Oh, I guess Duo's not working. Okay, Duo's not working. That's fine. I'll just do it on my virtual machine. So this is a virtual box. It gives me a Linux image on here I can use. Okay. Go away. Okay. So it's showing up okay? Cool. All right, so let's see, so I'm going to say copy. First, I'm going to go to my directory. I'm just going to copy mount. Windows desktop, home. Actually, lab1.spi.tar.dz. Okay, so I've got it here. So I'm going to untar it with tar zxvf. And the file is called lab_spi.tar.gz. Hopefully, I don't already have one here. Hold on, I might already have one. No, I don't. Okay, cool. All right, let's untar that. Okay, I'm going to the lab SPI directory. Okay, so in here, we have a code_C and a code_Python. You have to decide what language you want to use. I think last week most of you said you were going to write this in C. There was a few that wanted to use Python. Once you make that decision, you need to rename one of those directories as just code. Okay, so I'm going to say move code.c to code, right? And then you have to create a file in there, and this is all described in the lab sheet, by the way, but create a file in there called userid.txt. So I'm going to say cat redirect there, put my user ID in there, hit Control D. Okay, so now I've got a directory called code and a file in there called user ID. Now, if you go in that directory, you'll see there's already a skeleton in there for you, and there's a make file. So if you look at the main.c file in there, there we go. So there's kind of a skeleton here that you can start out with. It already has a line of code in there for creating the waves object for you. So it gets that from standard in. And then there is some log messages here, shows you how to do logging. And there's the free waves at the bottom, which is kind of redundant because that happens right before the program ends. And I think that's it. There's a for loop in here that allows you to read the signals out of there, but you may not necessarily want to do that. You may want to just go start scanning time. And by scanning time, I mean you'll have a variable, a time variable, and then you can initialize it to 0. And then, as I mentioned last week, there's two functions you can call. There's find next edge, where it'll find the time index of the edge of a signal, rising or falling, or both, or I should say either one. And then there's a signal at function, which will tell you the state of the signal at that time. So those are the only two functions you have to use for reading the file, and then you'll have to put loops in there to basically go through the files and interpret the values. Now, one useful tool for debugging this, and then there's also a grade script, that will actually just grade, that was not in the code directory though. There's a grade script that'll actually grade it for you, so you'll know what score you're going to get right away. There's also test cases that are in the test cases directory, and there's kind of a cool feature where if you run the grade script, there's an option called text to VCD, which will take one of those textual trace files that I showed last week, and it converts it to a VCD file, which stands for value change dump, which allows you to then open it up in a graphical waveform viewer called GDK wave. Okay, so you can just do grade.sh text to VCD, and then you have to pick one of the test cases. Now, if you look at the test case directory, there's a directory test cases, and it's split into the 3 parts. So there's part 1, that's where you're just reading single transactions. Part 2, which is the streaming. Part 3, which is MOSI and MISO. And then there is separate directories for each one of those test cases. So if I just take the first one, which would be part 1_001, and then I look at, there's the files in there. There's an input.txt. That's the only one you have to care about, input.txt. If you point to that, and then you give it an output name like waves.vcd, hopefully this will work. No virtual environment path. I guess. So the problem is, this will work on the lab machines. The problem is I just don't have this set up on my laptop. Let me just install that real quick. The grading, the auto grader tool is written in Python. Oh, well, Python and Bash scripts. Okay. Okay, so the first time you run that, it'll do a setup. Now this is one thing that's I can't quite figure out, but we can work around this. So there's a this is the thing I hate about Python, is that when we develop these tools, there's a package called Pi Digital Wave Tools. It's a module. And so when you run the script, it brings that down from pip. And it's a cool module because it's what allows us to generate, and not only generate the VCD files, but also read them too. You can actually go from text to VCD or VCD to text, right? The problem is that because that package, and this is normally how Python works, is that whatever the current version of that package is will be downloaded from the internet at the time you run it. So if the author of that package makes any changes, that could break the code that you've developed around that package, right? And in this case, they actually have a bug in there in that package that they introduced after we wrote the tools. And it's weird because it's a very simple bug. If you go in here to this file right here, so there's this file called writer.py, right? And I'm just going to take the whole path and I'm going to edit that. And you'll notice here that the error is on line 155. So if I go down to 155, you can see that they do this thing where they write to the value change dump and they write this time value. And previously, the format specifier for that was a D, right? It should be an F, and it is an F. And it is an F now because I actually patched it. I put a patch command in this grader script to automatically change it. But for some reason, even though that's been patched and fixed, there's some kind of a weird caching thing going on where Python won't recognize the change. So all you have to do is basically just change it again. So change F. This is the strangest thing I've ever seen. I'm going to change F to F and save it and exit. And now I run it, and now it works. In fact, now it's saying that my patch is rejected. But that's fine. So I've got, hold on a second. I might have to patch this again, actually. grade.sh. So let's just comment out that patch command. And yeah, so I might have to update this. Let's see if that works. Okay, there we go. Yeah, it works. So now we've got the waves.vcd. You can see that it's 81K. And then to read that waves, GDK waves.vcd. And so you get this thing. And this is a little intimidating at first, but if you just select root over there, there's your CFA, CPOL, MISO, MOSI, SCLOC, SS. You can drag those in. I forget, it won't let you drag them all in at the same time. Let's see. MISO, MOSI, SCLOC, and SS. Okay, so you drag those in, and you look at that and you say, oh, they're just, they're all just flatline. But that's because you have to zoom. You have MOSI. Yeah. Oh, sorry, thank you. Delete MOSI, delete MISO. There we go. Okay. You can see that here's the whole thing. So you can see that if you look at SS, remember slave select is active low. Okay, so every time that's low is a transaction. So you can see there's a whole bunch of transactions there. And then if you zoom in, yeah, you can see, so when there's no transactions, slave select is high and the clock is 0 because clock polarity is 0. And you can see the clock is only going while SS is low, and then MOSI and MISO are doing the thing there. And I can tell from looking at this is probably a read, because I can see some data coming back on MISO. Make sense? Okay, so that's how you can check the what's going on in there as opposed to trying to read the text files. And then the other thing you can do is, like I said, you can just type grade, and if you do just grade, it's going to give you the output of diff, which is going to compare the output of your code to the expected output of the correct answer. And so you might have not seen an output from diff before, but here you can see this is the actual output, which is nothing because the code was just running that skeleton, the little template or whatever. It didn't actually print anything with printf. It just printed to log, right? So if you print a log, it goes to standard error. So it goes into a separate spot. Your program should be printing out to standard out with just printf in the case of C. But this is what we expected to see. And you can see what it expected to see was a write to address 3F with data EF, a write to address 10 with F5, a write to address 12 with E1, and so on. So you can see there's quite a few transactions here, and they're all listed there. And this is just test case 1. Because it didn't pass test case 1, or test case 0, whatever the first one, it bailed out, right? So what'll end up happening is if your code is working, it'll run through all the test cases, and there's several hundred of them, right? Now there is an option for the grader script where it'll keep running even if one of them fails, but by default it'll stop if there's a mismatch, okay? And there is a log. Whenever you log, it puts the log in, I believe it's test cases part 1, 001. If you look at, I think it's here, an output.txt. Oh no, that's the expected output. I think it puts the log file in this directory. Actually, no, it didn't, because if it did, it would be in there, because there should be some logs. Hold on a second. Lab SPI, where does it put it? Logs, there it is. Yeah, there we go. So there's a logs directory, part 1, 001, and this will actually give you a make log. So if there was any compiler errors when it did the make file, they'll be in there, and anything that you log using the little log. You don't have to log, by the way. That's only for debugging. All we care about is the output, right? This is just all for testing stuff. You want to do testing. Any questions about that? Okay. So I will fix the grader script, and I'll post that on Dropbox. So you can still download that skeleton. I'll send out a corrected version of the grader script. But just so you know, like I said, the idea there is that if there's any weirdness there, basically the idea is that this grader script looks for a file called setupdone, which is just which you call a sigil that marks whether you've run it the first time. And this is setting up a Python virtual environment. And then I just added a command, a patch command there to patch. And by the way, part of that virtual environment is it installs this Pi digital wave tools. But then, like I said, the authors of that tool, wherever it comes from the internet somewhere, they put a bug in there. So this patch is supposed to fix that bug, and then that should have done it. But this patch file is a patch file I created. It just changes one line in that file. Basically, it just prints the time as a float instead of an integer. Okay? And of course, once you apply that patch one time, then you won't have any other issues. Okay. Anything else you want to mention here? Oh, yes, there's also a pack. If you do grade.sh --pack, it will create a submission file for you. And all you have to do is upload that to the submission box on Dropbox. So that way you don't have to worry about, it also, you know, it names it according to the user ID that you specified, and it puts lab 1 and the semester in there. It makes it a little easier for us to read those files. Okay? All righty. Okay, so let's go ahead and continue our previous lectures. So we were talking about, interfaces. So if you have an SPI interface that uses a push-pull circuit, and so if you have a shared bus, that could cause an issue if you have two drivers. Drivers are circuits that are on the chip that are actually that are emitting a 0 or 1 on an external wire. So with a push-pull, you're actively shorting that wire to either power or ground. And so if you've got two chips and one shorts the power, one shorts the ground, you end up with a short circuit. So that's going to end up sinking current out of, it's basically going to have a lot of current come out of one chip and get sunk into the other chip. If you use a tri-state buffer, you can avoid that, but the problem there is that then you have to be very careful that these guys coordinate and that only one of them has their tri-state buffer on at a time. In the case of an SPI shared interface, that shouldn't be too hard because the use case for this is you would have multiple slave selects, right? So only the master would only drive one slave, and so only that slave would activate its tri-state. So it should be fairly safe in that case, unless, of course, the master malfunctions and turns more than one slave select line on. Okay. Another option, though, that is is preferred for in some cases, this open drain. So open drain is where you don't have a pull up transistor, you just have a pull down transistor, but you do have a pull up resistor. And so that way, if none of the drivers on that wire, and again, I'm assuming that you've got multiple chips that are all outputting to the same physical wire in this case, if none of them are trying to, if none of them pull down, then the natural state of that wire is going to be a logic 1 because it's going to be, very close to VDD. It'll just be, what you end up with is a voltage divider here because when these transistors are turned off, they have an equivalent off resistance of 1 to 10 mega ohms when they're off. I mean, when you turn a transistor off, you think of it as off, it's disconnected, but in reality, it's just a very high resistance. So even if it's a mega ohm and you have a 10 kilo ohm pull-up resistor, you end up with a voltage divider that is basically 10 kilo ohms up to VDD, and then 2 parallel, in this case, assuming there's 2 drivers, there's 2 parallel resistors down to ground, which would have an equivalent parallel resistance of 500 kilo ohms. So now you've got a voltage divider with 10 kilo ohms up and 500 kilo ohms down. And so the voltage you would get there would be about 4.9 volts, which would still be very close to 5 volts. And in reality, these guys, I think, are probably closer to 10 mega ohms when they're off. So you'll get a little bit of a voltage drop there, but no big deal. On the other hand, if one of these guys pulls down, oh yeah, and then you'll get some leakage current there too, obviously, but very little, like 10 microamps in this case, if you solve the circuit equations. If you pull down, you also end up with a voltage divider where now you have the on resistance of one or both, right? Depending on if one of them is trying to pull down or both are trying to pull down. Let's just say one is trying to pull down. This guy will have an effective on resistance, say, of 1 ohm, right? So now you have a voltage divider with 10 kilo ohms up and 1 ohm down. So the output voltage is basically 0 volts, or very close to 0. And you'll get a little bit of leakage current there through that resistor, maybe about a half a milliamp in this case with these values. And then if you turn on both, if these guys both turn on their transistors, they're both pulling down, meaning they're both trying to talk at the same time, so there's a conflict. That's not catastrophic because now you just have about an equivalent of 2 resistors in parallel down to ground, and then with a voltage divider with this 10 kilo ohm up. So you end up with very little bit more leakage current, but not a big deal. Okay, so generally with this, these pull-up resistors can be outside the chips, they could be external, or they can even be internal, depending on the case. I2C is the next interface we're talking about, which stands for inter-integrated circuit, and it uses this open driver design, and it has 2 signals only. It has one called SDA and one called SCL. These names are going to be more consistent than the ones with SPI because SPI is not as strongly standardized as I2C. I2C is more of a strict standard. So with I2C, these names are almost always SDA and SCL. SDA stands for serial data, SCL stands for serial clock. So basically, if you compare it to SPI, SPI has S clock and I2C has SCL. That's the equivalent signal. Okay, so they're both synchronous buses. And then data it only has 1 data line, so I2C is half duplex, meaning that unlike SPI that's full duplex, you've got data channels going both directions. Even with UART, you've got data channels going in both directions. I2C doesn't. It just has 1 data channel, which is okay because if you remember in SPI there were 2 channels, but we only used 1 at a time. There was never a case, at least I've never seen a case where SPI uses both directions simultaneously. So it's kind of a waste. So SCL says, look, because this is designed for a transaction type protocol where I'm reading or writing, where I have to send the address first and the data comes next, might as well just have a half duplex, 1 data line. And then there's no slave select because I2C, instead of slave select, it uses basically a start bit, stop bit style interface like UART did. Like I showed you guys with UART. You remember that? UART had a start bit and a stop bit on the data line that indicated the start and end of a transaction in I2C. So as a result, we only have 2 wires. And so it's kind of a hybrid approach between UART and SPI. So it's serial, synchronous, half duplex, open drain style design. And it's also, unlike UART and SPI, it is a multi-master bus because it's going to take advantage of this open drain technology to allow anyone to be the bus master. So now you don't have assigned rules anymore. Any entity that's connected to these 2 wires can take mastership of the bus, right? Because anyone's allowed to send signals on either wire because of this open drain technique. Right? Okay, so I already mentioned that. Okay, so I2C has a packet format or a transaction format that's kind of a mashup between UART and SPI. It starts out with a start bit, but it's not really a start bit. It's more of a start signal, like a start condition. And I'll talk more about that in a minute, but it has a start signal. Then there's a 7-bit address. Okay, now the start bit and the address are going to be set on the bus by the master. Whoever's taking mastership of the bus will put out the start bit and the address, and then a read or write flag, which is much like SPI, that it has to indicate whether it wants to read or write. Okay, now this is where things get a little crazy because at that point, the master releases the data line. It keeps control of the clock, but it releases the data line. And it allows the slave to send back an acknowledge signal. So this acknowledge signal is only meant to acknowledge the address and the read-write bit. That's it. So this is a way for the master to know if anyone's listening or if anyone's responding to that address. Because the idea is that you're going to have multiple potential masters and slaves hanging onto that bus, and everyone's going to have an address. And so when you send out this address, what you're really doing is calling out to some endpoint that has that address. And if that endpoint is there, it's going to acknowledge that address, and you'll know he's there. If he's not there, then there's no point in continuing. You're like, no one's listening to me. Apparently that peripheral dropped off the bus, right? Okay, then after that point, if it is a write, okay, meaning that bit here was a 0, because you see a little tick mark after the W. That means write is 0, read is 1. If it was a write, then the master will seize back control of the data line and send 8 bits of data. And then it'll surrender the line again and have the slave acknowledge the data, right? On the other hand, if it's a read transaction, the slave will then keep control, because remember, the slave already had control at this point in order to send its acknowledgement of the address. It's now going to send its data back, and then the master will acknowledge, right? So in other words, the first acknowledge bit is always the slave acknowledging the address. The second acknowledge bit can either be the master or the slave, depending on whether it was a read or write. You guys make sense? So what you have here is the master always has control of the clock. The data line, though, it switches control. So it starts out, the master has the data, then the slave gets the data to acknowledge. Then, if it's a read, the slave keeps control, sends the data, and then gives it back to the master for the acknowledge. If it's a write, the master takes control again after the acknowledge, and then the slave takes control for the acknowledge of the data. Okay, so how many times does control change hands here, right? It changes hands once for the acknowledge, right? And then it changes hands only for the second acknowledge if it's a read, right? If it's a write, control of the data line changes hands on this acknowledge, it changes hands on the data, and then it changes hands again on that acknowledge. So if it's a read transaction, the data line will change control the entity in control of the data line will change 3 times. If it's a write, it'll only change twice, right? But like I said, the clock is always controlled by the master. Now there is a caveat to that though. There is this cool thing in I2C where if the slave decides that the master is running that clock a little too fast, or it needs some more time to think, it can actually do a technique called clock stretching, where, remember the open drain basically says that either side can pull down that signal. So the slave can actually pull the clock down as a way to tell the master to hold up, to stall, right? To wait, to chill, to slow down for a little while. All right, we're not going to do that in this class, but that's a neat option that is there. But in the simplest case, it's always the master that's controlling the clock, and then the slave just runs with that clock, right? Make sense? Okay, so I already talked about that. Okay, so here's an example. Now, another thing, I think the last thing here that could be a little confusing is this start signal. Well, 2 things. Hold on, back up 1 minute. So first of all, remember with SPI was an edge-triggered, used an edge-triggered clock, right? So we talked about how CPOL and CIFA were basically designed to have both sides agree on what edges of the clock to grab data, because they fundamentally were using flip-flops to read the data. You guys remember flip-flop? Hopefully you covered flip-flops in 211. Flip-flops use the edge of the clock, basically whenever the clock is changing from low to high or from high to low, depending on if it's rising edge or fall. It doesn't really matter if it's rising edge or falling edge, but the point is that it uses that change to capture data on that change, right? And then I mentioned that there is a setup and a hold time where you have to keep the data stable for a little bit before the change and a little bit after the change, right? When I say change, I mean edge, right? So that's edge triggered. Then you might have talked about these things called latches in 211. A latch is a level sensitive, right? Where basically when the clock is, say, high, data will transparently flow through it, and then when you drop the clock, it freezes whatever was in there, whatever the last thing that passed through, right? That's level sensitive. And we also talked about this in terms of interrupts too. Interrupts can be level sensitive or edge sensitive, right? Well, I2C uses a level sensitive clock. It uses a latch-based clock. Okay, so the idea is that whenever that clock is high, that's when you send data through. And then when you lower the clock, that locks in the data, and that's also when the data is supposed to change. So the data changes when the clock is low. It's supposed to remain stable when the clock is high. So clock is high, it's like you open a gate, right? You open like a gate, and you can get data through when the clock is high. When the clock is low, you close the gate. That allows you to change the data, so the next time you open the gate, the new bit goes through, right? So what that means is that the data should never change when the clock is high. The data should only change, all of these data transitions are when the clock is low. The only exception to that is the start and the stop bits, signals. Okay, so the start and the stop is the one time where, notice the clock is high and the data drops, it goes down, it changes, right? It has a falling edge. That falling edge happens while the clock is high. The only time that's allowed to happen is a way to indicate to the bus that something significant is happening. I am changing the data while the clock is high. That means it's a start signal, right? Likewise, the stop signal is when the clock goes high basically to its idle state, and then the data goes high to its idle state. That's the stop signal, right? So now keep in mind that this is the open drain bus, meaning that if no one's driving, if no one's touching the bus, it's going to be high. And when I say bus, I mean both of these wires will always be high when no one's touching it. In order to bring it down to 0, that takes an active, pull down from somebody on the bus, right? So the idea is that if there's no transaction happening and the bus is idle, it's going to be 1 and 1. They're both going to be active high because it's, no one's pulling down, everyone's just chill. And these guys are high because of that pull-up resistor. That pull-up resistor, which is a passive device, is going to make that bus, those wires look like they're active high, logic 1, right? So that's the idle state of the bus. And so when I want to go from idle and I want to turn the bus on, basically to take mastership, I'm just going to take the data line and drop it, right? While that clock is high, and boom, that activates the bus, right? And at that point, now obviously, as you might imagine, there's going to be some logic in there for detecting collisions. Because what happens if two masters do that at the same time? These signals are both inputs and outputs on all the chips that are on the bus. So they're driving these wires with the pull-down transistors, but they're also sensing the voltage of those wires too. So they can sense a collision. So there's a mechanism that comes into play if two devices try to pull down and start a transaction at the same time, right? Just like there is on Ethernet, for instance, right? But I don't even know how that works exactly. I think there's, it's in the protocol guide somewhere. But if we assume there's no transaction, you start it up by dropping the data line while the clock is high. And then at that point, the master does its thing where it'll set up the data and pulse the clock. Set up the next bit, pulse the clock. Set up the next bit, pulse the clock. These bits are arranged from most significant to least significant. And like I said, there's a 7-bit address and a 1-bit flag and an acknowledge. So what that means, if you count the clock cycles, there's 9 bits in the header, 9 bits in the data, but there's the 2 acknowledgements. So there's actually, I'm sorry, did I say 9? 8 bits here, 8 bits there, but there's the acknowledgement, which makes it 9 bits here, 9 bits there. So there's 18 total kind of clock cycles, clock pulses. 18, right? There's 9 and 9. It's in 2 phases, 9 and 9, but it's just really 8 plus 1, 8 plus 1, because it's 8 plus the acknowledge, 8 plus the acknowledge. Make sense? Okay. Okay. Okay, so here's an example. This is my my generator thing. So the question is, what's going on here? Well, this is pretty easy to read because you basically just have to look at each one of these clock pulses and just read the bit on the data line. I mean, you can also verify too, in fact, you should verify that the start signal is correct, right? The start signal is, just remember, don't change the data when the clock is high unless it's a start or a stop. Well, in this case, clock is high, change that, that's a start, okay? Now, from that point on, all I have to do is look at the data when the clock is high, ignore the data when the clock is low, because that's when it's in its state of change, right? So basically 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 0, 1, 1, 8, right? And then there's the acknowledge, right? Okay, and then, so if I back up from the acknowledge and look there, I think that's the read or write bit, if I counted correctly, right? 1, 2, 3, 4, 5, 6, 7, 8, yeah. The eighth bit, right? Yeah. And so that's a 0, which means write. Right, the data is 0 there, right? So this is a write transaction. So this is like, remember with SPI, you could kind of tell if it's a read or write depending on whether MOSI or MISO was doing stuff in the second exchange. Here, you don't have that, you don't know who's driving. From the waveform, you have no idea who's driving the data line. It's unclear. So you have to, the only way to know is to then find where that read-write bit is and figure out if it's 0 or 1. It's basically just the eighth bit. Okay, so here's the start bit, change the data when the clock is high. And then we have the address, which is 1, 2, 3, 4, 5, 6, 7 bits, right? So the address is 7 bits. It's, and again, it's most significant to least significant. Read-write bit, in this case, the read-write bit is 0, so it's a write. And then the acknowledge, by the way, is a 0. So if the slave that I'm trying to talk to isn't on the bus, is not listening, then obviously the acknowledge will be 1 because no one will be there to pull that open drain bus down, right? So from that, you should know that, yeah, the acknowledge is active low because active low means that someone's actually there pulling it low, right? So yeah, because this guy, you have to actively pull low. And then, so the acknowledge looks good, it's low. And then because it's a write, that means that the master now is going to take control of the data again, and I'm going to set the data is going to be 0, 0, 1, 1, 0, 0, 0, 1, and then the slave will take control and acknowledge that, and there's your acknowledge, and then the master will release the data, will release the clock first, let it go high, and then release the data second, which will indicate stop condition. So, keep in mind that with UART, the start and stop bits were actual bits. Were actually values during a bit slot, a bit timing slot. Whereas with I2C, it's not really a bit so much as a kind of a violation of the rule that you shouldn't change the data when the clock is high. Okay? Okay. So what is the stop condition of I2C? Okay, so this one is rising edge of the data when the clock is high. I think that's the one, right? Am I right? Yeah. Okay. Okay, so I already talked about this. Who's in control? Okay, any questions about I2C? Okay, so if you understand SPI and UART and I2C, those are I think a nice kind of base knowledge. You can kind of learn almost any protocol once you know those. There's a few miscellaneous ones I wanted to talk about. There's JTAG. JTAG is used for testing and debugging. So this is like, JTAG was developed I think in the 70s, and the idea is that when you make a chip, you need a way to basically read out the internal state of the chip, or set the internal state of the chip, right? So a way to basically think of it like a software debugger where you can go in and inspect what's going on inside the state of the program. That's what JTAG is for. Now you might say, wait a minute, that would be wildly expensive to do that, right? I mean, chips are fundamentally limited in their I/O pins, right? Because the real estate of a chip, grows as a square, right? The width times the height. But the I/O pins are, they have ball grid arrays now, but back in the day, you were kind of you had pins just arranged around the edges of the chip. So, the size of the chip, the internal area of the chip would grow much faster than the I/O pin count, with older chips. And so like if you needed to read the whole internal state of the chip just for debugging, that would eat up all your I/O pins. So JTAG was the solution, and the solution was that JTAG is a serial protocol, and it uses this technique where you basically connect all of the internal registers, at least in concept, in this gigantic shift register. So if you want to read what's inside the chip, you just shift all the bits out one at a time in sequence. Now the trade-off there is that it's going to take forever to do that. Very slow process, but that's okay because it's just used for testing. And usually when you're doing this, the chip is frozen. It's at like a breakpoint, it's frozen. And you can read all those bits out, and it only takes essentially one pin, right? So in one pin, you get access to the entire internals of the chip. That's the concept anyway of JTAG. And so JTAG is a standard that it's got a bunch of options. Usually when you see JTAG, there's only 4 pins, but there's some optional pins. There's something called test data in, test data out, test clock, so it's synchronous obviously, and test mode select. And when you look at that at first, you might say, wait a minute, that's SPI. It's the same thing as SPI. This is test data in is MISO, test data out is MOSI, test clock is S clock, and TMS is the slave select. Well, not exactly. It looks like SPI, but it's actually much different in the way that it works. So the idea is that not only can you read everything inside a chip with one pin, but you can also extend it to multiple chips. So you can build what's called a JTAG chain, which is where you can actually, and this is normally done on a circuit board. So you have a circuit board, and you got all these chips on the circuit board, and you have a big shift register in each chip, but then the output of the shift register from one chip just feeds into the next chip, right? And then finally, and so on and so forth, and it comes back. So this kind of looks like the daisy chain configuration of SPI, the multi-slave SPI thing that I showed you. Except in this case, the master is a computer. The master is some kind of a workstation that's debugging these chips, right? So the master is not shown here. These are all essentially slaves if you think of it in terms of like the multi-slave SPI. Okay, so the test data in comes into one chip, test data out comes out of that one, and then it sort of feeds through, it just snakes through like a big daisy chain, right? Much like SPI. The TMS and the T-clock are fanned out. So the master just controls both of those, and they're fanned out, which again, the daisy chain SPI work the same way, right? Okay, but the main difference though between JTAG and SPI is the way that you actually do control, how you send addresses in. And this part is kind of wild. So instead of the test mode select being like slave select, where it just goes down to activate the bus and goes up to deactivate the bus, this one is actually a bit that goes into a state machine that are on the chips on the bus. And by toggling test mode select with a certain pattern of bits, you can put the chips on the JTAG chain into one of 16 states, depending on the pattern of bits you send in. So this ends up being, so basically the default state is called test logic reset. And then there's two important states in here. One's called shift data register and one's called shift instruction register. So the idea is that you put when you want to interact with the JTAG bus, you put the chips into the shift instruction register first, okay? Once it's in there, you use the test mode, the test data in to shift bits in that will go inside the instruction register, right? In those chips. The instruction register is equivalent to the SPI address or the I2C address. The advantage of this though is that instruction register could be as long as you want it to be, right? Because once you get it into that state, you can have that instruction register be 1,000 bits, right? You just put it in there and then you start shifting bits in like crazy. And then when you're done doing that, use the test mode select to exit that state. And then likewise, once you set up the instruction register, then you go into the shift data register state, and that allows you to shift more bits in that correspond to the data that are operating within the context of what instruction you put in. So basically, this shift instruction register allows you to put the JTAG chain into a particular mode, and then once it's in that mode, then you start shifting in bits for the data. So this is how FPGAs are configured, by the way. You put the FPGA into a FPGA configure state with the shift instruction register, and then once you have it in that state, you put it in the shift data register and you shift in the bit stream for the FPGA, and that's what configures the FPGA. So if you guys were wondering, like when you took 313, why does it take so long to program the FPGA? I mean, I get USB is slow, but still like megabits, right? And you look at the program file for the soft file, right, that you guys generate is only about a few megabytes, right? So it should only take a few seconds to program the FPGA, but it could take a while. And the reason is because, you know, it's one bit at a time, right? So, you know, the number of, and you have to put it into there's some overhead to get it into the right mode. So basically it takes 8 times longer than you would expect it to take. Okay, so how do you get in these states? Well, the idea is that the test mode select is binary, but by using that in combination with the clock, because it's also clocked, you can put a sequence in. So let's say I want to go to the shift data register state. How do I do that? Well, I just put in, I have to get there. I get there by putting in a 0 first. That gets me down here. And then a 1, that gets me here. And then a 0, 0, right? And that gets me to the state I want to be in. At which point I could keep putting in zeros, and this loop back will keep me in that state as long as I keep putting zeros for test mode select. Now you might say, whoa, wait a minute though. Wait, How do you know you started in the test logic reset? How do you know that's where you started? How do you guarantee that that's the start state? Is there a reset on this thing or something? No, there's no reset, but if you set the test mode select to 1 for at least 4 cycles, it's guaranteed to return back to that no matter where you started from. So let's say I started from, I'll pick a random state. Let's say I'm here, right? If I set test mode select to 1 and keep it at 1, I'll go here, then I'll go here, and then back to there. So like if you set test mode select to 1, I think it's the maximum is 5, right? Is that what I have there? Yeah, 5. If test mode select is 1 for 5, at least 5 cycles, 1, 2, 3, 4, 5, it's guaranteed to go back to that test logic reset. And then once I'm there, then I know what state that those devices are on, and then I can just give it another sequence of bits and go to whatever state I want to go to after that. Does it make sense? So the idea is that test mode select is used to put me into a state. Once I'm in that state, then I use the serial, what's it called, TDI, TDO, test data in. I use the test data in to, shift bits in a particular context. And then you shift bits in, and then it's also shifting bits out. So basically, you're getting input and output at the same time. I can shift bits into the FPGA, but at the same time, the FPGA is shifting bits out that I'm reading. So you're doing an exchange like SPI does. Except it's not just 8 bits, it's an arbitrary number of bits, right? I'm not limited to 8-bit exchanges like SPI is. These things can be millions of bits, which they are on the FPGA. In the case of the FPGA, they're millions of bits I'm shifting here. Okay, so there's a few specific instruction registers that are defined. There's the ID, and this is pretty kind of cool, is that the JTAG defines a specific instruction as the ID register. So if I want to know what's on the JTAG bus, all I have to do is put it into the instruction register read state, right? And that state diagram is standardized, by the way. So I'll use a sequence of TMS bits to get it into the instruction state, and then I put in the ID register instruction, and then I go switch to the data register state, read in the data, and that'll tell me who's on the bus. It'll give me like an address, like a vendor ID, right? You guys heard of vendor IDs, like a MAC address, like a hardware address. So that way, I can take, like if you go inside the Quartus programmer, which you guys use in 3.13, and you hit Pro Bus, it'll actually show you, I don't know if you remember this, but it'll show you graphically what's on the bus, right? It'll tell you how many chips are there and what their IDs are. You might be like, how's that work? I didn't know that. It did that by essentially reading the ID registers of the JTAG chain. And then there's also a bypass register, which just shifts things through. And then there's a boundary scan. There's different, instructions that are built into the standard. Okay. Okay, and then finally, there's 2 other protocols you should be aware of. One's called CAN, the Controller Area Network. And this one is very similar to I2C. It uses the open, it uses the data line with CAN. There's 2 wires. There's a wire called CAN high and CAN low. And those ones are either, basically, there's either a voltage put between them or they're disconnected, right? And that's how you represent zeros and ones on a CAN bus. So it's a little bit different than I2C, but the packet format is very similar. It uses a very similar transaction format to I2C. It's a little bit more complicated, though. It's a longer. There's actually a longer. It has a CRC, a cyclic redundancy check error detection code. Unlike the simple acknowledgement mechanism that I2C has. So the packet format is longer. It starts to look a little bit more like USB. In fact, it's almost like CAN is almost like a mixture between I2C and USB in a way. But it's used for, it's very commonly used in vehicles. Cars use CAN buses, batteries use CAN bus. But if you understand I2C, you can very easily pick that up. And then I2S is a digital audio format, which is also like I2C, except it has specific bits that are geared towards the left and right audio channel. Okay, so just to summarize this stuff, we looked at I2C, SPI, and JTAG, and UART. This table just compares the three of those. So I2C is half duplex, SPI is full duplex, JTAG is full duplex. Although JTAG, you don't have to have both wires connected. If you just want simplex, one direction, you can literally just disconnect one of the UART line. Oh, sorry, I was thinking UART. JTAG. JTAG is full duplex in a way because you're shifting in and shifting out. Right, but with UART, you can disconnect the receiver or the transmitter line. The performance of these guys are all fairly similar. I2C has specific speed modes, but generally it's less than 3.4 megabits per second. JTAG is usually megabits per second. SPI is usually megabits, single or double digit megabits per second. And then, SPI and JTAG are push-pull, whereas I2C is open drain. I2C has a specific word size, 8 bits associated with it, whereas these guys don't, as I mentioned, SPI and JTAG. Although SPI usually is 8 bits. Addressing is I2C has a fixed addressing mode, whereas these guys are a little bit more flexible. And then I2C has 2 pins. These guys both have 4, although JTAG has some optional pins. And I2C is the only one that has an acknowledgement. Although JTAG, you kind of get an acknowledgement because if the JTAG chain is broken, you're not going to get, anything back. So you have to complete a chain in JTAG. Okay, that's it for that. Any questions? Okay, cool. Let's jump to the, let's see, we've got just a few minutes left. So the next topic I'm going to cover is FPGA design. So some of this will be a review from 313. So I'm going to go through this pretty quickly. But we want to start using the FPGA boards as platforms for doing some projects in here. We might switch in the last project to an Arduino or a Raspberry Pi. But for the next 2 projects, we'll be using the FPGA. So you guys remember from 313 and 6, do you all take 313 and 611, right? We changed the prereqs now. Okay, so FPGAs are programmable logic devices. I'm sure you remember that. We're going to use the same board again, the TerraSiC. In this class, so the objective here is we want to combine the tools from 313 and 611. We want to do them both now. So in 611, you guys just did purely hardware design. So you wrote your whole CPU in Verilog, right? And then you just pretty much just design everything from scratch. The problem with that approach is that you have to design everything from scratch. You can't use other like off-the-shelf IPs, intellectual property blocks, right? So that's not very practical. In reality, the way it generally works is you would make designs, but then you'd want other people to be able to use your designs, kind of plug them into the system. So if you remember from 313, you guys didn't do any Verilog design. You just started with the kind of a plug and play kind of system, the platform designer, where you had a system and you just dropped in IP blocks, right? So you might have been wondering, like, well, how do I combine these 2 approaches? Like, what if I want to build my own IP block? Like, for example, what if you wanted your processor that you design in 611 to be able to communicate with all the cool peripherals that you had in 313, like the VGA and what else did you guys? I guess that was basically it, right? VGA. We stopped using the flash. We used to use the flash chips on there. Oh, well, the DRAM, right? You guys used the DRAM in 313. You might have not realized you were using DRAM, but you were, because when you guys loaded your software in from 313, that was actually a fairly substantial block of code, because you had like your code plus the BSP code. And so that wouldn't fit on-chip memory. You had to use the off-chip memory for that. And so that's why you had to put the DRAM controller in there, right? And then for the VGA, you guys use the SRAM, I think. We still do that? The SRAM for the video memory. So we had a separate, like main system memory and video memory. And you had interfaces for those on your platform. But you guys couldn't use those in 611, right? In 611, you just had on-chip memory. You didn't have any ability to use off-chip memory. So the question is, how do we get the best of both worlds? How do we be able to build components that we can, like system Verilog components, that we can drop into that platform designer, either as a CPU design or as a kind of a peripheral design, right? So that's the objective of this class, is to, well, one of the objectives is to try to tie those two things together. And at the same time, get to practice software-hardware interfacing. So let's see. So we're going to start off with just building a new project like we did in 313. I'm going to run through this pretty fast. We could just call it lights, and then you open up your platform designer and you add components. You guys all remember this? Now you only did this once or twice in 313, so you might take some time to refresh your memory on this. This is kind of an arduous process because you have to go in and build up a base system design, and it takes some time because there's a lot of things you have to put in and then connect. But then once you have them all in there, then you just keep kind of either writing software for them, or in the case of this class, we're going to put some hardware in there too. But setting up that initial base design is kind of a pain, unfortunately, which is why some classes like this, they'll just give you the base design pre-made, which we could do that too. Or we could give you a Tickle script that will actually automate this process. You could just run the Tickle script and the Tickle script will add all this stuff and connect everything together. But I think there is some value in understanding what that stuff is and how it relates and how it's connected, and it doesn't really take that much time to do. The only problem is that it's prone to errors. So if you forget a connection in here, nothing works, and then it's like, well, what do I do now? It's very hard to track those kind of errors down. But that's why we're helping you in the lab. We have the TAs here. Okay, so we're going to add the processor, the interface to the DRAM, the clock manager. We're going to add the weird clock source you now have to add for the latest versions of Quartus. We're going to add the JTAG UART. The JTAG UART is, this thing is kind of crazy because it's UART, which is a text console, running over top of JTAG, right? And then that runs over top of USB, and it goes through the USB blaster. So this thing actually is a stack of 3 protocols, right? But basically the idea is that it gives you just a console on your workstation, so you can print messages from your CPU. Okay, then we'll add the SDRAM phase lock loop, and that's because, I don't know if Rasha explained that to you, but the CPU has multiple clocks in it, which is pretty common. There's a core clock for the CPU, and then there's an SDRAM clock. The thing that's confusing is that in this class, they're both the same speed, 50 megahertz. So you might say, well, what's the point of having 2? I don't get it. It turns out, and I don't entirely understand why this has to be this way, but the SDRAM clock, even though it's the same frequency as the core clock, it has to be at a different phase. They have to be out of phase from one another. Okay, so that's the reason why you have to jump through some hoops to set this up, because if you have them in the same phase for whatever reason, if the memory, and by the way, that SDRAM clock goes straight to the SDRAM chips. You just export it right out of the FPGA, goes directly to the SDRAM. But if that's on the same phase as your system clock, it causes some kind of timing issues, which are not apparent until you start getting glitches and bugs, or it misbehaves. So that's the reason you have to have that. And then you set things up, and then you end up with this. So here's what the completed design looks like. And so you've got the clock source. This is just basically an input port for the clock. There's the Neos 2 processor, which is a MIPS-based processor. So similar to RISC-V, It's not exactly MIPS. It's very similar to MIPS that you learned about in 212. Then there's the SDRAM controller, and then there's that SDRAM phase lock loop that creates that phase differential. And then the SDRAM clock component, which is just a port. Essentially, it's just an export that to the chip, the off-chip memory, and then the UART. Now, one thing you'll notice here is that this IRQ has an interrupt that goes back to the NEOS processor. So this interrupt allows you to, for example, have an interrupt when you hit a key on the JTAG, like when a JTAG, when a UART byte comes in, like when you hit a keystroke on your console. Okay, and then you just generate that and it creates the whole design. Okay, so that's all I've got for now. When we come back in on Thursday, you guys will you'll have this Thursday, and next Thursday to just work in the lab and ask questions on Lab 1, the first project. I'll give a lecture on Tuesday. I want to talk a little bit more about this stuff, so by the time you finish Lab 1, we'll be ready for the next lab. Okay, so does that make sense? So this Thursday, I'm not going to lecture. Next Tuesday, I will lecture. The Thursday after that, we'll work in the lab, and then the lab is going to be due at the end of next week. Okay, make sense? Okay, sounds good. We'll see you on Thursday.